Imagine watching an astronaut fall toward a black hole. From your safe distance, you see them approach the edge, the event horizon. And then something impossible happens. They slow down. Second by second, they move more sluggishly. Their movements become glacial. Time itself seems to betray them. They reach toward the darkness but never cross the threshold. Not in 10 seconds. Not in 10 minutes. Not in 10 years. Not ever. You would watch them frozen at the edge of that cosmic abyss, suspended in time, for the entire remaining lifetime of the universe. Meanwhile, from the perspective of the astronaut, they cross the horizon in moments and plunge toward oblivion. Both perspectives are true. Both are real. And the implications shatter everything we think we understand about reality, time, and the nature of existence itself. What if black holes do not work the way we think? What if the event horizon is not a boundary to be crossed, but a surface where time itself breaks down? What if everything we have ever seen fall into a black hole is still there, frozen at the edge, compressed into an infinitesimally thin layer that contains the quantum information of entire stars? Today we journey through evidence that challenges everything we thought we knew about the most extreme objects in the universe. Prepare yourselves, we begin. In 1915, Karl Schwarzschild, a German physicist serving on the Russian front during World War I, did something extraordinary. While calculating artillery trajectories by day, he spent his nights solving Einstein's recently published field equations of general relativity. Within weeks, he discovered the first exact solution, a mathematical description of how space and time curve around a massive object. But the solution contained something troubling. At a specific radius, something Schwarzschild called the Schwarzschild radius, the equation seemed to break. Space became infinite. Einstein himself refused to believe such objects could exist in nature. For decades, physicists treated the solution as a mathematical curiosity, elegant on paper but impossible in reality. But in 1964, everything changed. A young physicist named John Wheeler was studying the death of massive stars. He realized that when stars 30 times the mass of our sun exhaust their nuclear fuel, nothing could stop their collapse. No force in the universe could prevent the crushing weight of gravity from compressing the core of the star down past the Schwarzschild radius. Wheeler needed a name for these collapsed objects. At a conference in 1967, he called them black holes. The name captured the public imagination instantly. But Wheeler understood something most people missed. Black holes were not just dark objects that pulled things in. They were tears in the fabric of space-time itself. Regions where the normal rules of physics ceased to apply. Places where, according to general relativity, time itself came to an end. Here is what the mathematics told physicists. If you watched an object fall toward a black hole from a safe distance, you would never actually see it cross the event horizon. As the object approached that boundary, light from it would become increasingly redshifted. Stretched to longer and longer wavelengths, the object would appear to slow down, gradually fading from view as its light shifted into the infrared, then radio waves, becoming dimmer and dimmer. But it would never disappear completely, not technically. The mathematics suggested it would take infinite time, as measured by your clock, for the object to actually cross the horizon. Think about that. Every piece of matter that has ever approached the event horizon of a black hole, every atom of every star that has ever collapsed, every particle that has ever fallen in, it would still be there, frozen at the edge from the perspective of the outside universe. Meanwhile, from the perspective of the infalling object, something entirely different happens. You cross the horizon in finite time, seconds or minutes depending on the mass of the black hole. You notice nothing special at the moment of crossing. The event horizon is not a physical surface. It is simply the point of no return. Beyond it, all paths through space-time lead inward. You could fire your rockets at full power trying to escape, but you would only succeed in reaching the center faster. Two observers, two completely different and contradictory experiences of the same event, both predicted by the equations of Einstein, both equally valid. This paradox haunted physicists for decades. How could both perspectives be true? The question seemed philosophical until 1974. That is when Stephen Hawking made a discovery that transformed our understanding. Using quantum mechanics, Hawking showed that black holes are not entirely black. They radiate. Particle-antiparticle pairs constantly form near the event horizon. Occasionally one particle escapes while the other falls in. The black hole loses mass through this Hawking radiation, eventually evaporating completely. The discovery was revolutionary, but it created an even deeper paradox. If a black hole evaporates, what happens to all the information contained in everything that fell in? Quantum mechanics demands that information cannot be destroyed. It is a fundamental principle of physics. But if the black hole evaporates away completely, radiating only random thermal energy, where does that information go? This became known as the black hole information paradox. It dominated theoretical physics for the next 40 years. Leonard Susskind, a physicist at Stanford, refused to accept that information could be destroyed. He argued that somehow the information must be preserved. But where? Susskind gave an answer that seemed radical. The information never actually crosses the event horizon. Instead, it gets encoded on the surface of the horizon, a two-dimensional membrane that contains all the quantum information of everything that ever approached the black hole. He called this the holographic principle. It suggested something profound. The three-dimensional volume of spacetime inside a black hole might be completely encoded in the two-dimensional surface of its event horizon. Like a hologram, where a two-dimensional surface contains all the information needed to reconstruct a three-dimensional image. The implications were staggering. If Susskind was right, then in some sense nothing ever really falls into a black hole. Every star and every planet and every particle that crosses the event horizon from its own perspective becomes encoded on the surface of the horizon from the perspective of the external universe. Both perspectives are real. Both are complete descriptions of reality. They just describe different aspects of the same underlying truth. But the evidence forces us to confront an uncomfortable possibility. What if the event horizon is not just a mathematical boundary? What if it is a physical surface? A firewall of incredible energy that incinerates anything attempting to cross it? This question would lead physicists to question everything they thought they understood about black holes and spacetime and the nature of reality itself. If information really does get encoded on the event horizon, we should be able to find evidence. And remarkably, we have. In 2019, the Event Horizon Telescope collaboration released the first direct image of a black hole. The supermassive black hole at the center of Galaxy M87, 65 million light-years away. The image showed exactly what general relativity predicted: a dark circular shadow surrounded by a bright ring of superheated matter. But look closer at that ring. The light comes from the accretion disk, matter spiraling into the black hole at nearly the speed of light, heated to billions of degrees. This matter releases X-rays and gamma rays and intense magnetic fields as it approaches the event horizon. Scientists discovered something remarkable about this radiation. The X-rays show specific spectral signatures, distinct patterns that reveal the composition and physical state of the infalling matter. And these signatures persist far longer than they showed. According to conventional models, matter should cross the event horizon in milliseconds once it gets close enough. The X-ray emission should cut off abruptly. But observations from the Chandra X-ray Observatory and the Gazemian M. Newton telescope reveal something different. The X-ray signatures fade gradually, over seconds or even minutes. The matter appears to linger at the edge of the event horizon, continuously emitting radiation as it slowly approaches the point of no return. Dr. Andrea Ghez, who won the Nobel Prize for observations of the supermassive black hole at the center of our galaxy, noted something peculiar in her decades of data. Stars orbiting extremely close to the black hole do not simply disappear when they get too close. Instead, their light becomes progressively more redshifted, fading gradually rather than cutting off suddenly. It is exactly what you would expect if time dilation near the event horizon becomes so extreme that matter takes an extraordinarily long time to actually cross from our perspective. But this represents just one piece of a much larger puzzle. In 2015, the Laser Interferometer Gravitational Wave Observatory detected gravitational waves for the first time. Ripples in spacetime caused by two black holes merging 1.3 billion light-years away. The gravitational wave signal was designated GEBU 150914. It lasted just 0.2 of a second. In that brief moment, physicists could trace the entire merger. Two black holes spiraling inward, their event horizons touching, merging into a single larger black hole. and then the final object ringing down like a struck bell as it settled into its final configuration. But here is what is remarkable. The mathematics describing this merger works perfectly from the perspective of the external observer. The two event horizons merge smoothly. The gravitational waves match predictions precisely. The final black hole has exactly the mass expected from combining the two original black holes, minus the energy carried away by gravitational waves. However, from the perspective of matter on the event horizons themselves, infinite time passes during this merger. The entire history of the universe from that moment forward would unfold in an instant of proper time. More evidence comes from an unexpected source, the spectrum of Hawking radiation itself. In 2016, a team led by Dr. Sabine Hossenfelder published calculations showing something important. If information is encoded on the event horizon, then Hawking radiation should not be completely thermal and random. It should contain subtle correlations, quantum entanglement between particles that encode information about what fell into the black hole. Several research groups have now calculated what these correlations should look like. The mathematics is extraordinarily complex, involving quantum field theory in curved spacetime, but the predictions are testable in principle. The challenge is that Hawking radiation from astrophysical black holes is incredibly faint, far too faint to detect with current technology. A black hole with the mass of our Sun would have a temperature of just 60 billionths of a degree above absolute zero. It would take 10 to the power of 67 years to evaporate. This is vastly longer than the current age of the universe. But here is where quantum physics offers a glimpse of hope: analog black holes. In 2016, Professor Jeff Steinhauer at the Technion Israel Institute of Technology created an acoustic analog of a black hole using ultra-cold atoms. Sound waves in this atomic condensate behave like light near the event horizon of a black hole. And remarkably, Steinhauer detected the analog of Hawking radiation. More importantly, his measurements showed correlations between particle pairs. Exactly the kind of quantum entanglement that information preservation requires. The analog event horizon was acting like a holographic screen, encoding information about the infalling sound waves. While these analog systems are not real black holes, they are governed by the same mathematical structures. The fact that they exhibit the predicted quantum correlations provides strong circumstantial evidence that real black holes behave similarly. The evidence extends beyond laboratory analogs into the realm of pure observation and mathematical proof. In 2012, physicists Ahmed Al-Meiri and Donald Marolf and Joseph Polchinski and James Silly published a paper that sent shockwaves through the theoretical physics community. Their argument is known as the firewall paradox. It suggested something radical. The event horizon might not be empty space at all. Their reasoning was mathematical but devastating. If information is preserved, and if quantum mechanics holds, and if no information can escape from inside the event horizon, then there is only one resolution. The event horizon must be a physical surface of extraordinarily high energy, a firewall. Anything attempting to cross the event horizon would not gently pass through into the interior of the black hole. It would be incinerated instantly by a wall of Planck temperature energy, 10 to the power of 32 degrees Kelvin, the highest temperature possible in physics. The firewall paradox forced physicists to question fundamental assumptions. Either quantum mechanics breaks down near black holes, or general relativity prediction of a smooth event horizon is wrong. Or information is destroyed, or something even stranger is true. Leonard Susskind and Juan Moldacena proposed a radical solution: Einstein-Rosen bridges equals Einstein-Podolsky-Rosen pairs. Their proposal suggests these are the same thing. That quantum entanglement is actually a geometric connection through spacetime. If they are right, particles that are quantum entangled are connected by microscopic wormholes. And the event horizon itself might be a vast network of these quantum connections, linking every particle on the horizon to its entangled partner that escaped as Hawking radiation. This means the interior and exterior of the black hole are not separate regions at all. They are quantum entangled aspects of the same underlying reality, connected by wormhole structures too small to traverse, but large enough to preserve information. The most remarkable discovery involves what is called the Page curve. In 1993, physicist Don Page calculated how the entropy of a black hole should change over time as it evaporates. Initially, entropy increases as the black hole evaporates and releases thermal radiation. But halfway through the evaporation process, the entropy must start decreasing if information is conserved. The curve forms a distinctive shape, rising at first, then reaching a peak, then declining back to zero as the black hole disappears completely. For decades, no one could derive the Page curve from first principles. The mathematics did not work. But in 2019, a group of physicists finally succeeded. Their calculation relied on quantum extremal surfaces, mathematical objects that describe how information is distributed between the black hole and its Hawking radiation. And crucially, these surfaces live on the event horizon itself. The calculation proved that information leaks out through quantum correlations in the Hawking radiation beginning at the halfway point of evaporation. Before that point, the interior of the black hole dominates the quantum state. After that point, the Hawking radiation dominates. But here is the profound implication. For the calculation to work, the event horizon must be a genuine holographic surface. Every bit of quantum information about the interior of the black hole must be encoded on that two-dimensional membrane. From the perspective of the external universe, nothing ever truly enters the black hole. Everything that falls toward the event horizon gets scrambled and encoded on its surface, then gradually leaks back out through Hawking radiation over cosmic timescales. From the perspective of infalling matter, it crosses the horizon and experiences the interior normally. Both descriptions are complete. Both are correct. They are simply different ways of describing the same quantum reality. Physicists call this complementary descriptions. Recent observations from the Event Horizon Telescope have revealed another striking feature. The event horizon appears to have structure. High-resolution images show fluctuations in the brightness of the photon ring surrounding the shadow. Variations that persist over time. These fluctuations might be quantum noise, the signature of information encoded on the horizon constantly shifting and rearranging as matter approaches and Hawking radiation escapes. The event horizon is not a static surface. It is a dynamic churning boundary where quantum information undergoes constant transformation. The evidence extends beyond theoretical calculations into observations that should not be possible if black holes worked the way we once thought. The accumulating evidence points toward a revolutionary picture of black holes, one that reconciles quantum mechanics with general relativity through a principle called black hole complementarity. Proposed by Leonard Susskind and his colleagues in 1993, complementarity suggests that black holes have two equally valid but seemingly contradictory descriptions. And both are true. For an external observer, nothing ever crosses the event horizon. Matter approaches and becomes increasingly redshifted, and eventually becomes encoded on the surface as quantum information. This information gradually leaks back out through Hawking radiation over timescales of 10 to the power of 67 years or more for stellar mass black holes. For an infalling observer, however, the event horizon is locally indistinguishable from empty space. You cross it without noticing anything special. You experience the interior and you inevitably reach the singularity at the center, where space-time curvature becomes infinite and physics breaks down. These descriptions seem contradictory. How can matter both stay on the horizon and pass through it? How can the black hole have both an interior and be entirely described by its surface? The answer lies in the most fundamental feature of quantum mechanics: the observer dependence of reality. In quantum mechanics, different observers can have different and incompatible perspectives on the same physical system, and all can be correct. This forces us to reconsider fundamental assumptions about the nature of space-time itself. Perhaps space-time is not fundamental at all. Perhaps it is emergent, arising from more fundamental quantum information, like temperature emerges from molecular motion. Dr. Mark van Ramsdonk at the University of British Columbia has shown mathematically that space-time connectivity arises from quantum entanglement. Regions that are highly entangled are close in space. Regions with no entanglement are distant or disconnected. If Van Ramsdonk is right, then the interior of the black hole is generated by entanglement between particles on the event horizon and particles in the Hawking radiation. The interior is not separate from the exterior. It is a quantum dual description of the same entangled state. This connects to the holographic principle in a deep way. In 1997, Juan Maldacena discovered a precise mathematical correspondence between quantum field theories and gravitational theories in spaces, with one extra dimension. It is called the anti-de Sitter conformal field theory correspondence. This relationship shows that a three-dimensional quantum system can be exactly equivalent to a four-dimensional gravitational system. The extra dimension is the radial direction into the space. Black holes in the gravitational description correspond to high-temperature states in the quantum description. The event horizon corresponds to a particular surface in the quantum system. And crucially, all the information about the interior is encoded in the boundary quantum theory. Leading physicists now believe that black holes are the key to understanding quantum gravity, the long-sought theory that unifies quantum mechanics and general relativity. Dr. Netta Engelhardt at the Massachusetts Institute of Technology has developed a precise mathematical framework for how information flows between black holes and their Hawking radiation. Dr. Ahmed Almeri at the Institute for Advanced Study has shown that the black hole interior can be reconstructed from the Hawking radiation using quantum error correction codes. These are the same mathematics used to build quantum computers. The event horizon acts like a quantum encoding device, scrambling information in a specific way that allows it to be recovered. These are not just abstract mathematical games. They are precise predictions about how quantum information behaves near black holes. Predictions that will eventually be testable as our observational capabilities improve. The philosophical implications are profound. Reality itself depends on the reference frame of the observer in ways we never imagined. The next decade promises revolutionary observations. The Event Horizon Telescope collaboration is working toward creating videos of black hole event horizons. Time-resolved observations showing how the photon ring and shadow change as matter flows in. If the event horizon is truly a holographic surface encoding quantum information, these observations should reveal specific signatures, fluctuations in brightness, patterns in the polarization of light, and correlations between emissions at different wavelengths that encode information about infalling matter. The Laser Interferometer space antenna, scheduled to launch in the mid-2030s, will detect gravitational waves from supermassive black hole mergers. These mergers will allow physicists to test whether event horizons behave as quantum holographic surfaces during the most extreme dynamical events in the universe. Recent breakthroughs suggest we might even be able to detect Hawking radiation indirectly. While radiation from astrophysical black holes is far too faint to observe directly, primordial black holes could be detectable. These are tiny black holes that might have formed in the early universe. A primordial black hole with the mass of an asteroid would be about the size of an atom, but it would radiate at temperatures of trillions of degrees. If such black holes exist and one happened to be evaporating in our cosmic neighborhood, we could detect the burst of high-energy particles and gamma rays. Several experiments are searching for these signatures. The Fermi Gamma Ray Space Telescope and the upcoming Cherenkov Telescope Array are scanning the sky for the distinctive spectrum that an evaporating primordial black hole would produce. If we detect one, we will have direct evidence of Hawking radiation, and potentially the first opportunity to test whether the radiation carries encoded information as quantum theory predicts. But the implications extend far beyond black holes themselves. If the holographic principle is correct, then this might apply to the universe as a whole. Some physicists now propose that our entire observable universe might be a holographic projection from information encoded on its boundary. A sphere at the edge of the observable universe, roughly 46 billion light-years away. This does not mean we are living in a simulation or that reality is not real. It means that the three-dimensional space we experience might be an emergent description of more fundamental quantum information. Just as temperature is an emergent description of molecular motion, the mathematics works. The predictions are consistent with observations, and the implications are staggering. What this means for us is profound. We have discovered that the universe is far stranger than we imagined. Space and time are not the fundamental fabric of reality. They are emergent properties of quantum information. The distinction between inside and outside, between past and future, between here and there. These are perspective-dependent features of how we experience the universe, not fundamental properties of reality itself. black holes turn out to be windows into the deepest structure of reality. They are not just objects in spacetime, they are places where the nature of spacetime itself is laid bare, where quantum mechanics and gravity merge into something new and strange and beautiful. The universe is vast. The mysteries are endless. Recent breakthroughs in quantum information theory suggest that understanding black holes might be key to developing quantum gravity. String theorists and loop quantum gravity researchers are all converging on similar conclusions. Information is fundamental, spacetime is emergent, and black holes are the laboratories where these ideas can be tested. We stand at the threshold of a revolution in physics as profound as quantum mechanics or relativity. The next decades will determine whether these ideas are correct, whether the universe really is holographic, whether spacetime really is emergent, whether black holes really do preserve information through quantum entanglement across their event horizons. The journey has only just begun. The most profound implications emerge when we consider what black holes reveal about the nature of reality itself. If spacetime is emergent from quantum entanglement, then the universe at its deepest level is not made of particles or fields or geometry. It is made of pure information, quantum bits of information that generate the appearance of space and time and matter and energy. This suggests that the fundamental question of physics is not what are things made of, but rather how is information organized. Think about what this means. The chair you are sitting on, the air you are breathing, the planet beneath your feet. All of it might be patterns in a vast quantum information network. The appearance of locality arises from patterns of entanglement, not from space being fundamentally real. Black holes force us to confront an even stranger possibility, that the universe might have multiple equally valid descriptions that seem incompatible but are all true. From the perspective of someone falling into a black hole, they cross the event horizon and experience the interior and reach the singularity. Their description includes the black hole interior as a real region of spacetime. From the perspective of an external observer, nothing ever crosses the event horizon. There is no interior in their description, and all the information is encoded on the surface of the horizon. Both descriptions are complete. Both are consistent. Both are true in their respective reference frames. This is complementarity taken to its ultimate conclusion. Reality itself is observer-dependent, not just in the usual sense of quantum mechanics, but in the very structure of space-time. The unsolved mysteries deepen when we ask what happens at the singularity at the center of a black hole. General relativity predicts that space-time curvature becomes infinite at the singularity, that all infalling matter is crushed to infinite density in an infinitely small point. But physicists know this prediction cannot be literally true. It signals the breakdown of general relativity itself. Quantum gravity must resolve the singularity somehow. Some proposals suggest the singularity is replaced by a Planck scale structure, a region where spacetime itself becomes discrete and quantum mechanical. Others propose that the singularity might be a gateway to another universe, or to another region of our own universe. We do not know. And from the perspective of the external observer, we can never know directly. The singularity is hidden behind the event horizon, causally disconnected from the outside universe. Perhaps the most mind-bending possibility connects to the multiverse. If every black hole interior is causally disconnected from our universe, and if those interiors contain entire regions of space-time, then every black hole might contain a universe of its own. Some calculations in quantum gravity suggest that our universe itself might be the interior of a black hole in a larger parent universe. The Big Bang might have been the formation of that black hole from the perspective of the parent universe, while from our perspective it is the beginning of time. This is not science fiction. It is a legitimate proposal in peer-reviewed physics literature, though highly speculative. The mathematics is consistent with observations, though far from proven. The most disturbing implication involves the ultimate fate of information in our universe. If the universe expands forever and eventually reaches heat death, then the final state will be filled with black holes that have evaporated, leaving behind only faint Hawking radiation spreading through infinite space. But if information is preserved, then all the information about every star and every planet and every person who ever lived will be encoded in that radiation, scrambled across the entire future light cone of the universe. preserved in quantum correlations that span cosmological distances. In principle, that information could be recovered. In practice, it would require technology and energy resources beyond imagining. But it means that nothing is ever truly lost. Every action and every thought and every moment of existence leaves an imprint on the quantum state of the universe that persists forever. Your existence makes a permanent difference to the informational content of reality. We return to where we began. That astronaut falling toward the black hole. Frozen at the edge from our perspective, experiencing crossing the horizon from theirs. Both perspectives are true. Both are complete descriptions of reality. The contradiction is not a problem. It is a profound feature of how the universe actually works. What we have learned is that reality is richer and stranger and more beautiful than we imagined. Space and time are not the stage on which the universe performs. They are part of the performance itself. Emergent from deeper quantum structures we are only beginning to understand. We have journeyed from the Wardham calculations of Schwarzschild to the cutting edge of modern physics. From the first theoretical predictions of black holes to direct images of their event horizons. From the information paradox to holography. From firewalls to complementarity. From quantum entanglement to emergent spacetime. The evidence has accumulated over decades, each piece fitting into a larger puzzle. Black holes are not just cosmic vacuum cleaners or dead stars. They are the most sophisticated information processors in the universe. Quantum computers operating at the Planck scale. Holographic screens encoding everything that falls into them. The current scientific consensus is remarkable. Information is preserved. The holographic principle is correct. Black holes are quantum holographic systems, and spacetime itself might be emergent from quantum entanglement. What remains unknown is vast. We do not know the exact mechanism of information recovery. We do not know precisely how quantum gravity resolves the singularity. We do not know whether the firewall paradox means event horizons are truly smooth or hide high energy barriers. But we know black holes have revealed that the universe operates according to principles far stranger than we imagined. The boundary between inside and outside, between observer and observed, between information and geometry. These are not sharp divisions but complementary aspects of a deeper quantum reality. We have learned that to understand the universe we must abandon our intuitions about space and time being fundamental. We must embrace the observer dependence of reality. We must accept that seemingly contradictory descriptions can all be true. This is humanity's quest. To understand the universe not as we wish it to be, but as it truly is. To follow the evidence wherever it leads, even when it challenges our deepest assumptions about reality. Black holes, these frozen stars hanging at the edge of eternity. They have been our guides into the deepest mysteries of existence. They have shown us that the universe is quantum mechanical at its core, holographic in its structure. And stranger than we can imagine, the universe is vast, the mysteries are endless. But piece by piece, observation by observation, calculation by calculation, we are learning to read the quantum information encoded in spacetime itself. The journey continues, and the most profound discoveries may yet lie ahead.